Welcome to this video lecture. Myself Atul Kumar, working as an assistant professor in Department of Computer Science, Rajiv Gandhi Memorial, Government College, Jogindanagar. In this video lecture, I will discuss about stack organization in view of computer architecture. So, before discussing stack organization in computer architecture, firstly I will discuss what is stack. So stack is one of the important data structure that is used by the CPU, and the most important characteristic of stack is LIFO. LIFO means last in first out, means that if the element is inserted in the stack, then the last element that is inserted in the stack that is removed first. So item to be stored, or the element that is stored in the last position, is the first item that is to be accessed or removed from the stack. So this one is a kind of a stack. This one is the stack of books. Similarly, we have in computers, we have a stack and stack type of data structure, and there are two operations that are to be performed on the stack. That is, one operation is push operation and the second operation is pop operation. There is also a stack pointer top that points to the last element that is inserted in the stack. The push operation means to insertion or insert the element in the stack. The pop operation means to remove or delete the element from the stack. So suppose in starting the stack is empty and it contains suppose 5 elements. So it is the size of stack here is 5. So the size of stack is 5, and suppose we want to insert a new item in the stack. So by push operation we can insert a new item. So suppose the first item that is to be inserted in the stack is 6. So 6 is inserted in the first position, and now the top point to this position. Suppose this the address of this position is 0, the address of next position is 1, 2, 3 and 4. Suppose now we want to insert or push the next item, and suppose the next item is 1. So next item, to insert a next item, firstly the top, that is initially 0 pointing to 0, it is incremented by 1. So top is incremented by 1, so now top becomes 1, and push 1, insert a item 1 in that position. Now the top is pointing to this second position, that is 1. Again, suppose we want to insert new item. Suppose the new item is 113, push. So then the top is firstly incremented to 2, and again the item is inserted by the push operation. Now the top points to this top is equal to 2. Now suppose we want to remove the item. So we know stack follow LIFO, that is last in first out. So the pop operation will delete or remove the item from the last item that is to be inserted in the stack, and the last item inserted in the stack is 113. So the result of pop is 113, and now the top is decremented, and now the top points or stack pointer points to this position 1, and the item at stack position 1 is 1. So this is all about stack. So there is a term stack pointer in the stack that I have discussed, that is a pointer that points to the top position of the stack. So stack pointer is a register where the address of the stack is held. It always points to the top item in the stack, like in this figure. This point, if we delete 113, so it points to the top item, and the top item is 1, so it points to the stack pointer points to the top item of the stack. So there are two operations that are to be performed on the stack. One is push operation and other is pop operation. Push operation means insertion of item, and pop operation means deletion of the item. There is a stack pointer that I have discussed that point to the top position of the stack. Next, what is a register stack? So a stack can be placed in two ways in the memory. The one way is that it can be placed in a portion of large memory. The other way, it can be organized as a collection of finite number of memory words or registers. So how to implement a stack in computer organization? So the organization of 64-bit register stack is shown here. So this one is a 64-bit register stack starting from 0 and to 64. So the first position is 0, second position is 1, third position is 2, and so on. DR means here data register. There are two flags in the implementation of stack. One is full flag, and it is 1 when the stack is full, and empty stack, and it is 1 when stack is empty. There is also stack pointer that is of 6 bits in this implementation of stack, and it points to the top position of the stack where the last element is inserted in the stack, and it is of 6 bits. Why this one is of 6 bits? Because the size of stack here is 64, and 64 means 2 raised to power 6. So to address 64 positions of the stack, we need, or a stack pointer need 6 bits. So to address 64 bits, stack pointer needs 6 bits. That is why the size of this stack pointer is 6 bits. So here in the previous slide, we have 3 elements are inserted, A, B and C in the stack. So let us consider the stack where 3 elements are placed in stack A, B and C. Item C is in the top of the stack, as you can see in this. Item C is the top of the stack, and above this the stack is empty so that the content of stack pointer is pointing to stack 3. So stack pointer is always pointing to the top of the stack or the last element that is to be inserted in the stack. So C is the last element, so stack pointer pointing to the last element, that is C in the stack. So to remove the top item, the stack is popped by reading the memory word at the address 3. Firstly, we have to read this item, and then stack is decremented. The content of the stack pointer is decremented. So item B is now the when item C is removed. So now the stack pointer start pointing to item B, and item B is the top of the stack. Stack pointer is decremented to 2. To insert new item, the stack is pushed by incrementing the value of stack pointer and writing the word in the next higher location in the stack. So in this diagram we can see the size of stack is 64 bit. As I have discussed earlier, due to 64 bit we need the stack pointer of size 6 bits, as 2 raised to power 6 pointer is equal to 64. So it starts from 0 the first position is 0 and ends at 63. So the last position is 63, and in binary 63 means 6 ones. When we increment 63, then it again results in 0. By this demonstration it is cleared, when 1 is added to 6 ones, the result is 1 0 0 0 0 0, as stack pointer always accommodate the least significant bits, so the result is 0. This means if suppose the stack is full, and suppose the stack pointer points to this last position and all the other memory locations are full, when next item is inserted in the stack, then it again incremented, and the incrementation is like this. When we add 63 means in binary triple one plus 1, it results in 0. So as we just consider the least significant bits here. So again the stack pointer after this points to the first 0th position in the memory. So initially stack pointer is cleared to 0, so empty is set to 1 and full is also set to 1. So these are the micro operations for push and pop in case of that is to be performed in the computer organization. So for push operation, the micro operations are like this. Firstly, we increment the stack pointer. SP is equal to SP plus 1. Then we write the item on the top of the stack. When the stack pointer is incremented, at that address we write the item from the data register, and then we check if the stack is full or not. Then mark the stack not empty by writing empty is equal to 0. This one is the micro operation for push operation in the stack. To implement a micro operation in for pop operation, firstly read the item from the top of the stack, and the micro operation is like this. Just read the item from the memory to the data register, that is DR, and then decrement the stack pointer. The micro operation for this is SP is equal to SP minus 1, and then it will check, we have to check if SP is equal to 0, then mark empty is equal to 1 to check whether it is empty, and also to check whether stack is not full. So this one is the micro operation for pop operation in the stack. This one is the memory stack, resulting we have here three parts of memory. First part is program, second part is data, that is a operand, and the third part is a stack, and it starts from 4001, that is the starting address of the stack, and then it grows in the direction as shown in the diagram. Then 4001, then 4000. This means that the memory address is decremented, and the stack pointer here points to the top position of the stack where the last element is inserted. AR is the address register that points to the data in the memory, and PC is the program counter, and it stores the next address instruction, next instruction address. So in the figure, the portion of the memory, as I have discussed, partitioned into three segments. The first segment is program, the second is data, and third is stack. So the PC means program counter gives the address of the next instruction in the program and is used during the fetch phase. So fetch cycle phase, program counter address is used. Next is AR. AR is the array of data that is pointed by the address register and used during the execution phase. Next is stack pointer, that points to the top of the stack, pointer by the stack pointer, and is used to push and pop items. Next we have there are certain kind of stack limits in case of processor registers, and they can be checked with the help of two processor registers, one to hold the upper limit and one to hold the lower limit. So after push operation, when we insert a item in the stack, the stack pointer, the value of stack pointer is compared with the upper limit register, and if the value exceed the upper limit register, this means that the stack is full. And after pop operation, the stack pointer is compared with the lower limit register, and if the value is lower than the stack pointer is lower than the lower limit register, this means that your pointer is or your stack is empty. Thanks for watching this video lecture.